Hello, students. Stay happy, stay healthy. Today,
We are going to discuss about the most important topic, liquefaction of gases. This portion is deleted in JE mains, but they are keeping in JE advanced, right? So it is a gaseous state chapter, states of matter. For one is gaseous state, another one is liquid state. So in that liquid state, one of the portion is liquefaction of gases. Liquefaction of gases. So first, any gas, how we can liquefy? Any type of gas, how do we liquefy? Initially, gas is having the intermolecular space between the atoms is very far away. Intermolecular spaces are very far away. But when it converted into liquid, those spaces were decreased. Those spaces were decreased and attraction forces are increases. So here more attraction forces, less intermolecular spaces. That is what liquid. So what we need to do to convert the gas into liquid, we need to apply a more amount of pressure and we need to decrease the temperature. So simply for any gas to liquefy, what you need to do, you need to give a condition of high pressure and low temperature. This is the favored condition for the liquefaction of gases. Let's see. Here the piston is there. The container, we have a piston, weightless, frictionless piston. We are applying the pressure through the piston and the gas is compressed into liquid. Now here we are taking carbon dioxide gas. Let's see what are the conditions we are applying here. First one is at 10 degrees Celsius, 2 atmosphere pressure, it's a liquid state. The gas is converted into liquid at 10 degrees Celsius and 2 atmosphere. Now what I'm doing, I'm increasing the pressure. The moment I increase the pressure at same, sorry. Now what I'm doing, I'll increase the temperature slightly at same pressure. I'll increase the pressure from 10 degrees Celsius to 15 degrees Celsius and temperature remains and pressure remains same. In this case, the gas can be liquefied. No, gas is not liquid. What I will do at 15 degrees Celsius, what I have to do? I need to increase pressure also. Let's see, at 15 degrees Celsius, at 3 atmosphere, gas is in liquid state. Gas is in liquid state. Here also it is in liquid state. We can compress it. We can compress it. Now another condition, 25 degrees Celsius, 15 atmosphere. Yes, it is converting into liquid state. 30 degrees, 20 atmosphere. Very nice. Still it is converting into liquid. Now 35 degrees Celsius and 30 atmosphere. 35 degrees Celsius and 30 atmosphere. Can the gas can be liquefied? No. Gas is not liquefying here. Sir, maybe pressure is not sufficient. Maybe pressure is not sufficient. Let's try to give some extra pressure. Apply some more pressure. Now at 35 degrees Celsius, I am giving 35 atmosphere pressure. Can the gas liquefy? No. Still it is not liquefying. I'm giving extra pressure of 40 atmosphere. Same temperature 40 atmosphere. Still the gas is not liquefied. 50 atmosphere I had given. Still the gas is not liquefied. At 50 atmosphere also gas is not liquefied. So when that means at 35 degrees Celsius, whatever the pressure you give, the gas cannot be liquefied. Gas cannot be liquefied. Is that clear? Next, to discuss more about, so here the condition is 30 degrees to 35 degrees. So in this case, what conclusion you can give? Whatever the pressure you may apply at 35 degrees Celsius, the gas is not liquefying. So where the problem is occurring at 30 degrees Celsius, yes, it is in liquid state. At high temperature, high pressure, it's liquefied. But beyond that, if it reach 35 degrees Celsius, whatever pressure you may apply, it won't. Then now we'll see where the gas last time liquefied at 30 degrees Celsius, 20 atmosphere. Now I will increase the temperature slightly. 30.1, 20 atmosphere, yes. 30.2, yes, it's liquefied. 31.1, it liquefied. 31.2, it's not liquefied. See this point. See this particular temperature up to 31.1, the gas is liquefied. Beyond that temperature, beyond that temperature, the gas is not liquefying. Whatever the pressure, whatever the pressure you may give, the gas is not liquefying beyond this temperature. That particular temperature is called, that particular temperature is called critical temperature. That temperature is only called critical temperature. Is that clear? So to explain about this, another scientist came, that is Andrews. Andrews isotherm. Let's see. This is the curve. By seeing this, definitely it is very difficult to understand. But let's discuss very clearly of this graph how it is. The first at point A and B. At point A to B is what? A to B is nothing but, in this graph, A to B is nothing but gas is present. And here what it is mentioned, clearly what it is mentioned, and point B to C is nothing but vapor plus liquid is present. Vapor plus liquid is present. Next, C to D onwards, whatever it is out of the region, whatever it is out of the region, C to D is liquid. Now here, by seeing the graph, when a gas is converted into liquid, what is happening? Volume decreases rapidly at the same temperature. Volume is decreasing rapidly. See in this case, if you see this graph, this is the gas. When gas converted into liquid, see the volume suddenly decreasing from B to C here. The gas volume is suddenly decreasing. Next point. As the temperature increases, high pressure is required. Now what is happening? See from the temperature, this is the curve at T1, this is at T1, it is at T2. As the temperature increases, the pressure is also required according to the previous data. According to the previous data, as the temperature slowly increasing, the pressure is also high pressure is required to liquefy the gas. As a result, the area of gas and liquid, this is vapor and liquid area, is decreasing. As the temperature increases, high pressure is required. That is the reason the area which is having vapor and liquid region is decreasing. Clear? So in this graph, we are observing the few things. When the gas converted into liquid, immediately the volume is reduced very rapidly. As the volume reduced very rapidly, then volume reduces rapidly at particular temperature. Now, another condition, if the temperature increases, pressure is also increases. Pressure is also increases. That is the reason the region of vapor and liquid decreases. The region of vapor. Next, let's see. We'll discuss every region properly. We'll discuss every region properly now. First, only the region A and B. Between A and B, what is present? A B region is nothing but a gaseous region. Only gas exists. And the region B and C, region BC, what is happening? Volume decreases suddenly. Volume decreases suddenly. B to C volume suddenly decreases. At what temperature? At the particular temperature. At a constant temperature. Because the gas suddenly converted into liquid. Both vapor and liquid exist in this region. Because gas and liquid exist in this region. Next, region CD. See this region CD? Liquefaction is almost completed, and in the C and D there is no gaseous particle. In the CD phase, no gaseous particle, only liquid phases exists. Therefore, there is no significant increase in the volume. Volume remains same here. Between C and D, volume remains same. Volume is not changing because almost it is reached into the liquid state. Next, by using these conditions we can discuss about the critical temperature. What is the critical temperature? Here we'll see from the graph. We need to discuss what is TC. What is TC? TC is nothing but critical temp. Now in this graph we need to focus on the critical temperature TC. What it is discussing about? The temperature above which gas cannot be liquefied. Whatever the pressure you may apply, whatever the pressure you may apply, but beyond this temperature, the gas cannot be liquefied. Whatever the amount of pressure increases, that is what, whatever the pressure increases, volume of gas volume of gas is not at all changing, because here there is no volume. There is no volume. That is what EC T4, T5, T6, those all temperatures not comes under a liquid state. Liquid state it won't possible. At T1 it is possible, T2 is possible, and T3 is also slightly possible. But beyond that, TC, between T3 and T4 we have TC. Beyond the, above the TC, whatever the pressure we may apply, gas cannot be liquefied. Below the TC, yes, gas can be liquefied according to the particular pressures. That is the concept behind this. Next, critical constants. It is defined as the temperature above which gas cannot be liquefied by applying any amount of pressure. By applying any amount of pressure, that is the TC. TC, yeah, it has been derived from the van der Waals gas equation, from the real gas equation. TC equal to 8A by 27 RB, where A and B are van der Waals gas constant. A corresponds to what? What is A representing? A represents what it is? A is corresponds to attraction forces. Attraction forces. If the A value is high, the gas can be liquefied easily. A is more means gas can be liquefied easily. And B is what? B is another gas constant. It depends on the size of the gas particle. Size of the gas particle. Next, it is given one is not TE, students, it's a printing mistake. This is, it's a TC. It is nothing but it is TC. Next, critical pressure PC. Critical pressure PC. What is PC? The pressure required to liquefy a gas at its critical temperature. The pressure required to liquefy a gas at its critical temperature. At critical temperature, how much pressure is required exactly to liquefy a gas? The minimum pressure, how much is required, that is what critical pressure. So given that Pc equal to A by 27 b square. Pc equal to A by 27 b square. Next, critical volume, this is Tc, this is Vc, critical volume Vc. Critical volume, the volume occupied by the gas at Tc and Pc. At critical temperature and critical pressure, the amount of gas, the volume of gas occupied is called critical volume. Vc equal to 3b. Next, critical point. What is this critical point? The critical point refers to the state of a system, state of a substance at critical condition. State of a substance at critical conditions. Critical conditions at the critical point. The densities of liquid and gas become same. The densities of liquid and gas become same at critical point. Another one, the boundary between liquid and gas disappears and there is no distinction between two phases. And there is no distinction between two phases. There is no boundary between gas and liquid. That's why it is. The boundary between liquid and gas disappears and there is no distinction between the two phases. That means there is no boundary between liquid and gas. That's the reason at this point both the phases can exist equally. The substance become a single phase. In this case, the substance become a single phase known as a supercritical fluid. Supercritical fluid, that is what above Tc, exactly above the Tc, a critical point is existing. There, a substance is present in supercritical fluid. A, a gas below its critical temperature is called vapor, and higher the critical temperature of gas, more easily it can be liquefied. Higher the critical temperature, more easily it can be liquefied. Here you see the comparisons. We have written the formula. Tc is directly proportional to A. Critical temperature you have seen. Tc equal is directly proportional to A. As the Tc is directly proportional to A, higher the critical temperature, higher will be the attraction forces. Higher the critical temperature of a gas, more easily it can be liquefied at a given temperature. As the A value increases, Tc increases. If Tc increases, liquefaction of gas also increases. Easily gas can be liquefied. The question we may expect from here. Next, compressibility factor at critical condition. What is the compressibility factor? Compressibility factor, you know, Z. Z is nothing but PV by RT. So here critical conditions they said, that's why we are taking Z equal to PCVC by RTC. PC we have A by 27B square. 3B is there. RTC is there. R into 8A by 27 RB. So after substituting everything, Z equal PCVC by RTC equal to what we got? 3 by 8. 3 by 8 value is what? Z is less than 1. Z is less than 1 means corresponds to the attraction forces. So, at critical conditions, compressibility factor is less than 1. That is nothing but it refers the attraction forces. That's the concept behind this. Next, Boyle's temperature, TB. Boyle's temperature is nothing but TB. TB, Boyle's temperature. It is the temperature at which real gas behaves like an ideal gas. At this particular temperature, both real gas and ideal gas behaves as the same only. That is what Boyle's temperature. At Boyle's temperature, PV is constant for a real gas over a long range of pressure. Generally, if you remember one graph, the PV versus P or V, the graph remains straight line for ideal gas. For ideal gas. But for real gas, the graphs are coming in this manner, no? Like this we did in this way, right? So for real gas, graphs came like that. But what it is telling that at this particular boils temperature, the PV value is constant. PV value is constant for both ideal gas as well as real gas over a long range of pressure. That is at boils temperature. At boils temperature, both real gas and ideal gas shows a similar type of graphs. Next, inversion temperature. Inversion temperature, Ti. It is the temperature above which a real gas on expansion shows heating, and below which on expansion it shows cooling. What a beautiful point here. In thermodynamics, it is the one of the finest application. What is it? It is the temperature above which a real gas on expansion, when a gas is expanding above this temperature, it shows heating effect. Below which on expansion it shows a cooling below this temperature. That is what inversion temperature. Above this inversion temperature, heating effect is showing on the expansion. Below this temperature, cooling effect is showing on the expansion. That is what formula is. They have a relation between boils temperature and inversion temperature. That is Ti equal to 2 TB. That is Ti equal to 2 TB. Right? For any ideal gas, critical temperature Tc is 0 Kelvin. That means inversion temperature also 0 Kelvin. But that means ideal gas cannot be liquefied. You cannot liquefy any original ideal gas. We are liquefying only real gases. That's the concept behind this. Next. Next, students, we need to discuss about the liquid state. Liquid state, what is that liquid state? In that liquid state, the few applications are there. Vapor pressure. Vapor pressure. Vapor pressure is the pressure exerted by the vapors of a liquid or solid when it is in equilibrium with its liquid or solid phase. Generally, when vapors are in equilibrium with both liquid and vapor, then it is called vapor pressure. Next, it is a measure of tendency of molecules of liquid or solid to escape from the liquid or solid phase and enter into the gaseous phase. What it is simply telling, in a gaseous condition, in a container, the gas is liquid is present. Suppose liquid is present. When the liquid is converted into vapors, it is in a equilibrium state. It is an equilibrium state with liquid, right? That is what vapor pressure. The pressure exerted by a vapors when it is in equilibrium with gas and liquid state, or else solid and gaseous state. And mainly, it is the measure of tendency of molecule of liquid or escape from the liquid. The tendency of escaping of gaseous molecule from the liquid or solid phase. That is what are the factors affecting vapor pressure. The first one, temperature. In class 9th you have studied already. In the liquid state, vapor pressure increases with temperature. This is because as the temperature increases, molecules of liquid have more energy and are more likely to escape from the liquid state. Next, surface area. If the surface area increases, vapor pressure is also increases. That is also very clearly. Next, intermolecular forces. Intermolecular forces. Vapor pressure decreases with increasing intermolecular forces. If more forces are there, it is difficult to vaporize the liquid. Next, second one. This is unknown one for now. You can study the surface tension also. In physics also you can study. In chemistry we have some theoretical definition only. Physics you will study more deeply about surface tension. So what is that? Surface tension is the tendency of a fluid to resist an external force that attempts. Tendency of a liquid to resist an external force that attempts to increase in surface area. It is caused by the cohesive forces between the molecules of liquid. Cohesive forces between the molecules of liquid. Surface tension is responsible for the formation of droplets, bubbles, and other shapes in fluids. Because of surface tension only, different droplets we are getting on the walls of container, on the surface of liquid, like that. Why, sir? Why surface tension is taking place in a liquid? Because the cohesive forces between the molecules of a liquid are caused by the intermolecular forces between the molecule. These forces can be van der Waals forces, or hydrogen bonds, or ionic bond. The stronger the intermolecular forces, greater will be the surface tension of the liquid. Greater will be the surface tension of the liquid. Cohesive forces are nothing but attraction forces between the molecule. These attraction forces are due to maybe van der Waals force, due to maybe hydrogen bond, or maybe ionic bond, right? As the cohesive forces are more, the surface tension is more, and its units are Newton per meter or Joule per meter square. That is the small information about surface tension. In the examination they may ask about rules and factors, units and factors. Next, viscosity. Viscosity, it is the property of fluid that oppose the motion between the adjacent layer. It is nothing but it is the property which oppose the fluidity of a liquid. Viscosity is nothing but opposite term of fluidity. Fluidity means what? The movement of liquid. Viscosity means what? Opposite. The property which resists the flow of a liquid is called viscosity. If the thickness is more, more viscosity. If thickness is less, less viscosity. Suppose we'll take example of oil and water. We'll pour the both oil and water on a floor. Which one? Which one can pass easily? Water can flow very easily because it is less thickness. That means less viscous. When the viscosity is less, its fluidity is more. Whereas in the case of oil, thickness is more, more viscous. More viscous means less flow, less fluidity tendency. That's the concept. It is a measure of fluid's resistance to flow. The higher the viscosity, more resistant the fluid is flow. Next, and its SI units are Pascal, Pascal second, or Newton second per meter square. Newton second per meter square. Next, some factors affecting this viscosity. Factors affecting the viscosity. The first one, temperature. Temperature. The viscosity of most fluids decreases as the temperature increases. Suppose if the temperature increases, molecules in a fluid move more quickly because molecules can flow very quickly, which makes fluidity is increasing, viscosity is decreasing. That's why. Next, pressure. The viscosity of most fluids increases as the pressure increases. As the pressure increases, the thickness is increases. The attraction forces between the layers of liquid increases. More closely packing takes place. As a result, viscosity is also increases. Next, composition. The viscosity of a fluid is also affected by its composition. For example, mixture of two fluids is typically higher than the viscosity of either of the individual fluids. Suppose individually I am taking the viscosity, after mixing of them, their viscosity is much more higher than the individual fluid. That is the concept behind this. Clear, student? This is about the concept of liquefaction of gases and liquid state. Thank you.